Throughout the exam, you're going to have to check for divisibility. It's a critical skill that's used over and over, whether you're factoring numbers, answering questions. So let's take a moment and look at our different options. Long division is one way we could always deal with that issue. But quite frankly, it takes time and uses a number of calculations that are prone to mistakes and errors. So it's not necessarily the best option on an exam that's time constrained without a calculator. Another approach I'll call, without a better name for it, I'll call it the guess and check method. And essentially what we're doing is choosing a multiple of the divisor that is close to the number you want to check divisibility on and easy to compute in your head. So what do I mean by that? Let's look at a real quick example. Say I wanted to divide 50 by 9 and check the divisibility of that. Well, I know 9 times 5 is 45. So right away, I've chosen a multiple of 9 that I quickly know already in my head is close to 50, and that's 9 times 5. So the difference between 50 and 45 is 5. So I have a remainder of 5. Now I want to check if that remainder is divisible by 9 as well. My original guess is a multiple of 9, and the remainder is a multiple of 9, then I know that original number 50 in this case is a multiple of 9. But of course 5 is not divisible by 9, that is not a whole number, so 50 therefore is not divisible by 9. Okay, that example might seem pretty straightforward and obvious. Let's look at another one that might be less obvious at first blush. So 403 divided by 13. Is 13 divisible into 403? Well, I could look at that and say 13 times 30, a nice round multiple of 10, is 390, and I know that gets me close to 403. So again, I'm going to look at the difference, and I'm going to check if that difference is also a multiple of 13. In this case, that difference is 13, which is, of course, a multiple of 13, 1 times. So I know my original number, 403, is divisible by 13. If that difference was 0, that means the number that I originally guessed as a multiple of 13 is the exact number I'm trying to check also. So in the case of 0 remainder, I'm finished at that point. I've done my divisibility check and it worked. That's the guess and check method. It's a general approach that will work for any numbers, any divisibility test. That said, we should also know our divisibility rules very well because they can be faster in many cases and they can actually help out for instances that are not easy to otherwise calculate divisibility for. So let's look at our divisibility rules for numbers 2 through 11. Of course, every number is divisible by 1. Let's start with 2 and some of the easier ones first. Any number that ends in 0, 2, 4, 6, or 8, in other words, an even number, is divisible by 2. 5 is fairly easy as well. Any number that ends in 0 or 5 is divisible by 5. It's an even multiple of 5, it ends in the 0. If it's an odd multiple of 5, it ends in 5. 10, any number that ends in 0 is divisible by 10. How about some of the others? Let's build up from our last digit check on 2. If we want to check 4, we want to look at the last 2 digits, and we want to check if it's divisible by 4. So for example, if I have 832, or even make it 8,832, all I need to do is check those last 2 digits. 32 is divisible by 4, that equals 8, so 8,832 is also divisible by 4. And as we go to 8, which is 2 times 2 times 2, 3 times, we want to, not surprisingly, check the last 3 digits for divisibility by 8 in this case. So let's take the same number and see how that works out. 8,832. I only need to check the last 3 digits, 832 in this case. Unfortunately, it's not always obvious whether a 3-digit number is divisible by 8 or not immediately. So if I look at it a little further, I might divide by 2, and then divide by 2 again, and then a third time divide by 2 yet again. So for 832 divided by 2, that's 416. 416 divided by 2 is 208. 208 divided by 2 is 104, or a whole number, which means 8,832 is divisible by 8. So I actually combined a couple rules here. I used the last 3 digits only, and then I did an iterative division by 2 because I know 8 has 3 2's as factors. So if I divide by 2 3 different times, I'm effectively dividing by 8. Let's go back to 3. 3, you simply sum the digits and check divisibility for the sum of the digits. So let's say I had 633. In this case, I would sum 6 plus 3 plus 3. That equals 12. And I know 12 is divisible by 3, so 633 is also divisible by 3. Why is this one pretty cool? Well, one, it's a quick check, and the number could be in the millions, the billions, and so on, and we'll still have a quick check for divisibility. 9 is also very similar, and not surprisingly, 9 is 3 times 3. So we again sum the digits, but this time we want to check for divisibility by 9. So if we had the same number, we would look at 6 plus 3 plus 3 again. We know that's 12, but divided by 9, it's not evenly divisible by 9. So that doesn't work, and 633 is not divisible by 9. It's also worth noting that a number divisible by 3 might not be divisible by a multiple of 3, like 9. But if the number is divisible by 9 going the other direction, it must be divisible by its factors, like 3. How about 6? Well, likewise, we know factors of 6 are 2 times 3. So to check 6, all we do is check 2 and check 3. So let's suppose we had a number like 998. Well, I'll check 2. It ends in an 8. It's an even number. That works. I'll check 3. 9 plus 9 is 18 plus 8 equals 26. But 26 is not divisible by 3. So my check does not work on 3, and therefore 998 is not divisible by 6. I need both checks to work. And unlike 8, I should also mention, we don't have to incrementally divide by 2 over and over 3 times, but you can check 2 and 3 on the same number. How about 11? 11's where things get really exciting. Kind of like 3 and 9, we're adding digits together, but in this case, we're adding the alternating sequence of digits and subtracting the opposite sequence of digits. So what do I mean by that? You want the first, third, fifth, seventh, ninth, etc. digits, sum them up, and then you want to take the second, fourth, sixth, etc., sum them up, and you want to subtract the one from the other to get the result. And you then want to check that result if it's 0 or a number that is divisible by 11. So let's see an example. How about 1001? Well, first I want to take my odd digits, 1 plus 0, and sum up that sequence. And I'm going to subtract the alternating sequence of digits, which is minus, in this case, 0 and 1, my second and fourth digit. And that just works out to 1 minus 1, or 0. And 0 is part of the check, so that does work, which means 1001 is divisible by 11. So that turns out, just like 3 and 9, to be a really nifty check we can use on very large numbers as well. 7, not my favorite, but it works as follows. If I have a number, say 842, what I want to do is take my last digit and double it. So double last digit and subtract that. In this case, that's 2 times 2 or 4, and subtract that from the remaining digits, 84 in this case. So 84 minus 4 is 80, and now I want to test 80 to see if it's again 0 or divisible by 7. 80 is not divisible by 7, so I know 842 is not divisible by 7. So real quick, it's helpful to recognize the groups of approaches for divisibility rules to remember them at the end of the day. The 2, the 4, the 8 rules are related. You're checking the last digit, the last 2 digits, the last 3 digits. 5 and 10 are very similar and simple. You're just checking for 0 or 0 and 5 as your last digits. The rule for 3 and 9, where things start getting really interesting, are the same. You're summing the digits together and then checking divisibility. And 11 is a variation of that, where you're summing the alternating sequence of digits and checking for 0 or divisibility by 11. And 6 is simply checking the factors. Check 2 and check 3, the factors of 6. 7 is a stranger rule that you may or may not choose to remember. Some of you students might be asking, wait a second, don't we ever have to check numbers greater than 11 for divisibility? The answer is yes, you do. For example, you might be required to check whether 409 is a prime number. And if you checked up through 11, I think you'll probably find that you don't have any number that divides evenly into 409. So do I then have to check all the way up to 409? Well, fortunately, no, you don't have to go nearly that high. Let's take a quick look at what we do have to check above 11. So we know there's no need to check even numbers because that would have already been picked up in the divisibility by 2. And expanding on that idea more generally, there's no need to check composite numbers because they would have been picked up with the divisibility by 3, 4, 5, 7, any of the numbers up to and including 11 up to that point. What we really need to check is only prime numbers above 11. So what are they? That's 13, 17, 19, 23, 29, 31, 37, 41, and so on. So how high do I have to go? You might be curious at this point. And the answer is you don't need to go any higher than the integer below the square root of the number in question, in this case 409. So I know 409 is greater than 400, and I know 400 is a perfect square. It's 20 squared, so that is an integer. And I know 21 squared is greater than 409, it's 441. So I don't need to go any higher than 20. Or among my list of prime numbers, which is the only thing I need to check, I only need to check these 3 for divisibility, at which point I'm absolutely certain 409 will be a prime number. So if I run a check on 13, 17, and 19, unfortunately in that case I'll still find none of them work, and I will realize that 409 is a prime number, but at that point I can say with 100% certainty that that is the case. The next part is optional, but I'm going to answer a question that may have occurred to several curious students out there. Do these rules always work? And if so, why? Well, the short answer is yes, they do always work for integers. And of course, when we're talking about divisibility, we are by definition dealing only with integers. And let's look at a few instances of why they work. And let's start with, say, 4. Why does the divisibility by 4 and the divisibility rule by 8 work? Well, if I had a number that's 632, effectively I can factor that out into 600 plus 30 plus 2. And I know anything times 100 is divisible by 4. So 100 is divisible by 4. Any multiple of 100, 300, will be divisible by 4. So this part automatically is divisible by 4, which means I'm only checking the last part, the 32. And if that also is divisible by 4, then my whole number will be divisible by 4. And the rule for 8 works very much the same way. However, in this case, 8 is not divisible into 100, not evenly. It's 12.5 times 8. But 8 is evenly divisible into 1,000, or 10 to the third is the lowest power of 10 into which 8 evenly divides. So again, if I have 14,632, the 14,000 part must be divisible by 8, because I know 1,000 divided by 8 is 125. So 14,000 divided by 8 is 14 times 125, which equals 1,750, a whole number result. So again, this part is divisible by 8. I only need to check my remaining 632, whether it's divisible by 8 or not. And right away, it doesn't appear obvious to me whether it's divisible by 8. So I'm going to divide by 2. 632 divided by 2 is 316. Divide by 2 again, that's 158. And divide by 2 again, that's 79. So therefore, it is divisible by 8. And my whole number, 14,632, will also be divisible by 8. Okay, the first part's pretty cool, divisibility by 4 and 8. But why does divisibility by 3 and 9, where we sum up the digits, why does that work? That seems even less obvious. Well, this one comes down to factoring. So again, if we want to look at, say, 633, essentially, that 6 represents, as we saw before, 600, or 6 times 100. I can factor that to 6 times 99 plus 1. And I know 99 is divisible by 3. It's 33 times 3. So my number 633 equals 6 times 100 plus 3 times 10 plus 3. We've learned that up to this point already. But now the clever trick is I'm going to factor it into components that are divisible by 3 and ones that may or may not be. So 3 is really just 9 plus 1 in this case. And of course, if I had a thousandth digit, I could make it 999 plus 1, or 10,000s, 9,999 plus 1. I keep going with this result of 9s plus 1 factoring. And then the units digit is, of course, just the units digit. So if we rearrange those, that's 6 times 99 plus 3 times 9 plus 6 times 1, which is 6, plus 3 times 1, which is 3, plus our units digit, which is just plus 3. In this case, this whole part is a multiple of 99 or 9, and I can pull out a 3 if I wanted to. I could distribute out a 3, which is another way of saying this whole thing is or must be divisible by 3. And that leaves the only thing to check as the sum of the digits, 6 plus 3 plus 3. So if this also is divisible by 3, then the result will be divisible by 3. So in this case, 6 plus 3 is 9, plus 3 is 12, which is divisible by 3. Therefore, we know this must be divisible by 3. We just determined this, the sum of the digits, is divisible by 3. Therefore, the whole number is, and in every case, will be divisible by 3. Kind of cool. How does that work for 9? Well, it effectively works the same way. Let's try the same number again. 633. In this case, it's 6 times 1 plus 99, plus 3 times 1 plus 9, plus 3, the exact same approach. And I know 99 is divisible by 9, the way I set up my factoring, and 9 is divisible by 9. So I can do the same exact approach for 9 as well. I'll rearrange my terms to those that are divisible by 9, the 6 times 99 and the 3 times 9. And what I'm left with is the 6 plus 3 plus 3, again, the summation of the digits of the number. And in this case, I'm checking for divisibility by 9. 6 plus 3 is 9, plus 3 is 12. And 12 in this case is not evenly divisible by 9. So that does not work, which means the sum of the digits is not divisible by 9, and 633 in this case is not divisible by 9. For those brave souls among you who are asking, how about divisibility by 11? Why does the alternating series of digits sum together and checking for 0 or divisibility by 11, why does that work every time? Well, it's a little more complicated, but actually really not too much so. It's basically boiling down to our second rule or approach for divisibility we learned earlier, which is to make a quick guess that's somewhere close to the number we're trying to check divisibility of, and then take the difference and check divisibility of that differences. And that works in general. We're going to use this same concept here as well. However, we have one added fact we need to take account of. Any odd exponent of 10 plus 1 is divisible by 11. So how can we prove that that's the case? Well, let's take a look just to see. 10 to the 1 is 10, plus 1 is 11. Surely that's divisible by 11. 10 to the third is 1,000, plus 1 is 1,001. And as we saw earlier in the example, that too is divisible by 11. In fact, it's 11 times 100, which is 1,100, minus 11 times 9, which is minus 99. And that gives us a result of 1,001 is 100 minus 9, or 91 times 11. And the same continues for 10 to the 5th, 10 to the 7th, etc. The odd exponent plus 1 must be divisible by 11. In a similar fashion, the even exponents, in this case minus 1, are always divisible by 11. And let's just check that that's true. 10 squared is 100, minus 1 is 99. And that, in fact, is 9 times 11. 10 to the 4th is 10,000, minus 1 equals 9,999. And that is 9 times 1,111. 10 to the 6th is 1,000,000, minus 1 gives us 999,999, and you can see a pattern developing. We have even numbers of 9s, therefore we know it's divisible. In this case, it's 111,111. So in these cases of odd exponents of 10 plus 1, all numbers are divisible by 11. In the case of even exponents minus 1, all numbers are divisible by 11. So let's go back and look at an example. Say we've got 4,632. And for 4,632, I can restate that as 4 times 10 to the third, or 4,000, plus 6 times 10 squared, as we saw before, 600, plus 3 times 10 to the 1, which is 30, plus our 2. And that essentially is our result of 4,632. That's the actual number. How about our guess? How are we going to use elements 1 and 2 to create our guess? Well, I'm going to do the following for my guess. I'm going to take the 4 times 10 to the third and make it 4 times 10 to the third, an odd exponent, plus 1, which I know must be divisible by 11, plus 6 times 10 squared, an even exponent, minus 1 in this case, will also be a number that's divisible by 11, plus 3 times 10 to the 1, and because it's an odd exponent again, I'm going to add 1 to it, and I know that's divisible by 11 as well. And the units digit I won't include because if there were the 2 or some other number added on, then my guess won't be divisible by 11. And I'm creating a guess that must be divisible by 11. And the process I'm going to use here is essentially the same process we learned earlier. I'm going to take the difference between the actual number and my guess, and I'm going to check for divisibility by 11 or 0. The case of 0 means the numbers are exactly the same, and therefore it certainly is divisible by 11. It helps to rearrange our guess and our actual number to see things more clearly. Now recall, our guess, by the nature of the way we create it, is a multiple of 11. So to work out the difference, as we would from our multiple of 11 guess versus the actual number, at which point we'll then check the difference to see if that is divisible by 11, we'll have to calculate this out. So hopefully this arrangement will help. And we're going to expand our expression for our guess. 4 times 10 to the third is 4 times 10 to the third, plus 4 times 1 is plus 4, plus 6 times 10 squared is 6 times 10 squared, plus 6 times negative 1 is minus 6, plus 3 times 10 to the 1 is 3 times 10 to the 1, plus 3 times 1 is just plus 3. So right away we can see our 4 times 10 to the third minus our 4 times 10 to the third just results in 0. 6 times 10 squared minus 6 times 10 squared, and again this minus is multiplied through the entire actual number, so that is positive minus, they cancel, plus 3 times 10 to the 1 minus our 3 times 10 to the 1, those cancel, which leaves us only a difference of 4 minus 6 plus 3 minus our 2. And as we can see, the original number was 4,632. This is our alternating sum of digits. We are adding the first and the third digit, and we're subtracting the second and the fourth digit. And that would work if we had a fifth, sixth, seventh, eighth digit as well. So now we want to check if this summation is 0, in which case my guess was the actual number, or a multiple of 11 itself. So let's add that up. And the sum is minus 1, which is neither 0 nor divisible by 11. So as a result, we can say 4,632 is not divisible by 11. But that is the general approach, and it's why in every case we end up, regardless of the number, the alternating series of digits and a check for divisibility by 11.